Hello, this is Lab 2 of Physics 2212, Lines of Change. For the introduction and the goals and findings, the goals were to investigate the distance dependence of a magnetic field of a small bar magnet, to measure the magnetic field of the magnet on-axis and off-axis using the Biot-Savart law for magnetic fields, and simulate a computational model and compare it to measured magnetic fields. The findings were that the magnitude of a magnetic field increases as distance decreases, making it inversely proportional. The magnetic dipole moment is approximately 1.488 am squared. The measured off-axis field is 7.45 e to the negative 5 teslas. The simulated off-axis field is 2.95 e to the negative 5 teslas. The Biot-Savart law relates magnetic fields in teslas produced by an object at an observational point to the current I running through the object and the distance between the source of the field and the observation point. The magnetic fields of, or dV for this section dl, is produced by the following equation. Far from the loop where little r is much greater than big R, and through the center of the loop, the magnitude of the magnetic field of the loop has the shape of the on-axis magnetic field of a dipole, and the magnetic field of the loop is modeled by this equation, and the dipole is measured by the following equation. The magnetic dipole moment is equivalent to the following equation, and the direction of the on-axis magnetic field is in the same direction as the magnetic dipole moment, which is the same as the direction of the conventional current I. Some more information. The magnitude of the magnetic field of the magnetic dipole on the perpendicular axis is as followed. The direction of the perpendicular axis is opposite to the magnetic dipole moment. The magnitude of the magnetic field due to the bar magnet is as follows. K is the combination of magnetic constants, and the equation is used to solve for magnetic dipole moment, and the general formula for the magnetic field of the dipole moment is the following. The visual model of the magnetic field to the right, and the system is the observational point, or the magnetometer. The surroundings is the bar magnet, which produces the field, and the magnetic field of the bar magnet is treated as a dipole. For the procedure, the materials needed were a bar magnet, a magnetometer, a meter stick, and a tape. Compensating for the magnetic north, orienting the phone such the magnetometer app has an x-component of 0. Then finding the magnetometer chip, measuring the on-axis magnetic field, which included measuring the on-axis distance between the magnetic and the magnetometer so that the magnetic field is 100 teslas. Record the y component of the Earth's magnetic field with no interference, making a vector, which is equal to 45 degrees. Measure the magnetic field at that point in components, and repeat the procedure 2 times. This was the data that was collected from the this was the data collected, and as you can see that an inverse proportion is shown. For the data analysis and results, the equation, the following is the equation which is, for the regression line. The slope of that line equals n, and the y-intercept is equal to the natural log of k. You solve for k using Euler's constant and an exponential function. Using constants derived from the line, we can derive the dipole moment equation. The corrected magnetic field in the y direction is calculated by subtracting the Earth's magnetic field from the measured y component of the magnetic field at the off-axis. These were our observations, and basically when the magnetometer is far away, the measured non-zero magnetic force in the x direction, and as it moves closer, then the magnetic field increases. This was the computational model for the constants of the magnetic field function. This was the arrow scaling and drawing of arrows for magnetic field. This was the off-axis magnetic field and magnetic field arrow. As for the discussion, as the distance between the magnetometer and the magnet decreases, the magnitude of the magnetic field increases, showing an inverse proportion, showing the following data. Magnetic dipole moment is equal to 1.4875 am squared. The experimental magnitude of the field axis is as follows, with a pretty large, or a larger magnitude relatively, and the simulated has a smaller, and which is an 86% difference in the net magnetic field from the experiment to the computational. Sources of error could just be distortions of the magnetic field from nearby devices, inconsistent placement of phones, leading to the inconsistent magnetic field measurements, surface inconsistency, measurement error, somewhere in there. As far as what ifs, what if you hadn't oriented your experiment to compensate for the magnetic north and instead laid out a meter stick at an indeterminate angle? This would basically make the both x and y components different, since the north would contribute to both of those, the z component wouldn't change. If you had two identical bar magnets together end to end and run the experiment again, the magnetic field would increase due to the combined magnetic fields of the two magnets. We expect magnitude of new magnetic field to be around double the magnetic field of the current bar magnet, and the measured distance for each of the field would decrease due to increased magnetic field from the two magnets.